Thank you all for coming out to hear a little bit about what I do. I've been given just a few minutes to share with you some of the work that led to this award. Basically, I'm really passionate about energy storage and specifically lithium-ion batteries. So today I'll tell you a quick story about a small part of my work on stabilizing these really high energy density materials in order to be able to use them in electric vehicle or portable electronic applications. So this should be pretty familiar, I think, or some of these names on here should be familiar to people. We have lead acid batteries that I think everyone has in their cars, conventional lithium ion technology. There's probably hundreds of them just right around here in our cell phones and laptops and these cameras. But if we want to move, this is on the x-axis energy per weight and on the y-axis energy per volume. So smaller batteries that hold the same amount of energy or really big batteries that hold even more energy than we can imagine right now. You need to go up on this graph here. And to do that, the key is really this lithium metal anode. So lithium is really the basis for all of these technologies. Right now we store it combined with some other materials. So we can store it with some metal oxides or some graphite. But when you have pure lithium metal, it can actually store about 10 times the capacity of these conventional materials that are in our pockets today. And to do that, you really have to stabilize this material because it's so high energy density, it's very volatile, very reactive, and so it's actually quite dangerous right now to use. And it's the basis for all these fires that you see going on in all these different battery technologies. And when we do successfully enable lithium metal, you see it actually approaches the energy density of gasoline. So we can have an electrochemical storage technology that is almost on par with chemical fuels, which is really a game changer for these sorts of materials. Just taking one example, specifically where these batteries could be useful is in electric vehicles. So here's plotted different battery technologies with their specific energy, but then also the driving range of a battery in a sort of car that you would put these in. So you start with lead acid, which is the most common. You get very short driving range, just maybe 30 miles or so, all the way out to today, our lithium ion technology, like a Tesla or a Bolt. Those are now over 200 kilometers, and we're getting very, very good. There's been really great progress every year improving the storage of these materials. But you can see there's this gap here to these future technologies, and that's where we really start to get competitive with gasoline-powered engines. You can have very far range and lower the cost of these vehicles so that they're accessible to a lot of people. And to jump that gap, again, the key is really lithium metal and enabling this very high energy technology. The way that I've worked on to enable this technology is with self-healing polymers. Self-healing is exactly like what it sounds. You make a cut in it, and just like your skin, it would heal itself. Our polymer heals a bit more quickly than skin. You can see on the top here, this is just over a minute. We punch a hole in the polymer, and in a minute, that hole has fixed itself. And so when we coat this material on lithium metal, that's on the side here, you'll see the kind of yellowish piece of lithium metal is coated with our polymer. The silver one is not. You leave it out in air, and very quickly, the lithium metal has reacted with the air, corroded, it's begun to decompose, even in 30 minutes. But with our polymer coating, you see it's quite stable. And so using this technology, we're able to stabilize this material and enable these batteries to cycle. Here's what an electron microscope image of these batteries look like up close. So this is on the micron scale after we've deposited the lithium metal into our battery. This again is without our polymer coating, and you can see it's very loose growth, very mossy structures, and that is what leads to the degradation. You have all of this surface area and this really poor quality deposition that leads to these dangerous problems that cause the fires, cause the short circuits, and cause these batteries to fail. However, with our polymer coating, you can see very thick, very dense deposition, so we have almost ideal cycling of these materials, meaning that they're very safe and very useful. Now, this was just one of our polymer coatings that we used. We also performed a really broad, sweeping analytical study to see what about these polymers was making them work so well so that we can design even better polymers in the future and really push this technology to market. And what we found was actually through a series of experiments, there's really two simple, easily measurable properties of a polymer that dictate how it will perform on these lithium metal coatings. And that's the surface energy, or how strongly it interacts with the lithium, and then the dielectric constant. That's how strongly it interacts with the lithium ions once they're dissolved into the polymer. And so when you have a very high dielectric constant, low surface energy polymer coating, you get really large, very nice and dense deposits of lithium metal. Using this understanding, we're able to walk our efficiency up from left to right. So this is that first polymer I showed you here on the the right at about 98% efficiency. So that's just every cycle you lose about 2% of the lithium, which is certainly not good enough to put in your cell phone or your car. Your battery would die in just 50 cycles, so 2 months of charging and discharging your cell phone. But we're able to go up using our understanding that we developed here to this new polymer that's over 99% efficient. And so as we continue to develop this understanding, continue to make new materials, we'll be able to improve this and hopefully enable this technology very soon. So with that, I'd again like to thank Metron for the opportunity to be here. This work wasn't done in a vacuum. I didn't do it by myself. My PhD advisors, Professor Jinan Bao and Yi Shui at Stanford, were integral in this work, as well as my postdoc advisor, Professor Yangsha Horn at MIT, and all of these people who worked very closely with me, specifically on the work I presented today. So I thank you guys for being here, and thank you for the opportunity.
Congratulations again. Thank you, Jeff. I want to thank everyone for joining us, most importantly giving Jeff a platform to share some of his research. Congratulations again, and thank you for spending some time with Metron. Have a great show. Bye-bye.